In this lecture, we'll take a closer look at how battery technology have evolved, what distinguishes various generations of batteries, and what defines a good battery from a performance standpoint. We will explore the specific material and formulation used in commercial systems, as well as the emerging chemistry expected to shape energy storage future. By the end of this module, you'll understand the trade-off between different battery chemistry and their suitability for various applications, from portable electronics to electric vehicles and large-scale grid storage. Batteries are typically grouped in generation based on the dominant technology and the level of performance they offer. First-generation batteries include the well-known lead-acid system, which are still used today due to their low cost and despite their modest energy density. Second-generation batteries introduced nickel-based chemistry like nickel-cadmium nickel-metal hydride, offering improvement in cycle life and energy density, and commonly used in early electronic and hybrid vehicles. Third-generation batteries are dominated by lithium-ion technologies, which have transformed modern energy storage with high energy density, long cycle life, and flexible design. Fourth-generation technology include solid-state batteries, lithium-sulfur, lithium-air, and post-lithium chemistry, such as sodium-ion, magnesium-ion, calcium-ion systems. This chemistry aims for safer operation, higher energy density, and lower cost of materials. When comparing battery technology, several key performance indicators must be considered. Specific capacity, the amount of charge per unit mass. Energy density indicates how much energy can be stored and is crucial for portability and for electric vehicles. Power density describes how fast the energy can be delivered. Cycle life is the number of charge-discharge cycles a battery can endure while retaining acceptable performance. Coulombic efficiency, how efficiently a battery stores or releases charge, ideally near the 100%. Safety includes resistance to thermal runaway, flammability, and abuse tolerance. Cost per kilowatt hour, a major factor for scalability. Sustainability includes material abundance, recyclability, and environmental impact. These KPIs are interdependent, and improving one often comes at the cost of the other. For example, boosting the energy density may reduce cycle life and safety. Current commercial battery systems use tailored formulation to balance the cost, safety, and performance. Lead-acid batteries are used in vehicles and UPS systems where the cost is critical. Nickel-metal hydride batteries power hybrid cars and electronics where toxic material restrictions are important. Lithium-ion batteries, which include various cathode chemistry like NMC, LFP, and NCA, dominate mobile electronics, EVs, and power tools. NMC, nickel manganese cobalt, offers high energy density and power density. LFP, lithium iron phosphate, is favored for stationary application and budget EVs, and for its safety and long cycle life. Lithium cobalt oxide is common in smartphones. Each formulation involves a specific combination of active materials, electrolyte, separator, and cell design, optimized for a user case. Manufacturers like Panasonic, CATL, and LG Solution lead the development and scaling of this technology. With every battery cell, the electrolyte and the separator play a vital role. The electrolyte serves as a medium for the ion transport between the electrodes. Lithium-ion batteries electrolytes are usually a mixture of organic carbonates like EC, DMC, with the lithium salts such as lithium hexafluorophosphate. The separator, typically a polyolefin membrane, prevents the direct contact between the electrodes while allowing the ion to pass. Electrolyte additives such as fluoroethylene carbonate enhance the performance by stabilizing the interface and improving longevity. However, liquid electrolytes are flammable, volatile, and sensitive to moisture. Next-generation solutions include the ionic liquids, dipeptidic solvents, and solid-state electrolytes, each aiming to improve the safety and electrochemical stability while reducing the thermal runaway risk. Solid-state batteries are one of the most promising emerging technology. The use of a solid electrolyte, polymer, ceramic, or composite mitigate the risk of leakage of combustion. The use of polymer electrolyte offers flexibility but suffers from room temperature conductivity. The use of ceramic electrolyte offers excellent conductivity and stability, but they are brittle and hard to process. Composite combine polymer flexibility with ceramic performance, improving interface compatibility. The other post-lithium chemistry includes sodium-ion, using sodium instead of lithium, promises lower cost and improved resource availability. Zinc-ion, magnesium-ion, and calcium-ion systems are being explored for aqueous batteries and beyond. Lithium-sulfur batteries offer high energy density but face issues with stability and the active material loss due to the shuttle effect. The choice of a battery formulation depends heavily on the application. Consumer electronics needs high energy density and compact form factor, typically lithium-ion with LCO and NMC cathodes. Electric vehicles need high performance and fast charging capacity. NMC and LFP dominate here, depending on performance versus cost trade-off. Grid storage prioritizes low cost and long calendar life. LFP and emerging sodium-ion batteries are being trialed for this purpose. Battery design must also consider charging speed, thermal management, mechanical safety, and integration with electronic or structural components. While lithium-ion batteries have enabled modern mobility and electronics, challenges remain: material sourcing, cobalt, lithium, and nickel availability, and ethical extraction, recycling, closing the loop for critical elements, safety, further reduction of fire risk and abuse tolerance. Emerging materials such as cobalt-free cathodes, low-cost sodium-ion, and recyclable solid electrolytes aim to tackle these issues. Research is focused on improving fast charging, reducing cost, and increasing sustainability. Major players investing heavily in solid-state battery pilot lines, while academic labs explore new electrolyte chemistry and battery architecture. In conclusion, battery formulation and performance characteristics have evolved alongside the needs of modern society. Each chemistry has brought new capability and trade-offs, from lead-acid batteries to lithium-ion and beyond. The future lies in balancing energy density, safety, cost, and sustainability through advanced system and system design. The success of battery technologies lies in identifying and integrating optimal materials and architectures that balance performance, safety, cost, and sustainability, tailored to the specific needs of each application, from portable device to electric vehicles and grid-scale storage.